Now, the equation for collecting gas over water isn't super complicated. It's just addition or subtraction. But for some reason, it seems to be a confusing concept for kids. So we're going to do a little bit more practice. We finished this one. So we're going to just do a little bit more practice. Oops. So we're going to collect a sample, or so solid potassium chlorate was heated in a test tube and decomposed. So we actually did this reaction earlier this week. The oxygen was produced by, collected by displacement of water at a certain temperature and then the total pressure. So I'm going to show you a picture before we kind of start on this. So there's a couple different ways to do this. Let me be so I can draw. In a lab setting. So this is one way. Looks like a kind of like just a jar. And so what you would do in this case is you would fill the jar all the way up to the top with water, and then you would dump all of that water in a graduated cylinder to know how much water makes up the jar. So then you know the volume of the jar. And then you would do the experiment. They're heating potassium chlorate. The oxygen gas is being bubbled in, and it's bubbling in, right, and displacing the water, so the water comes out. Okay, and then this empty space is considered to be assumed to be the oxygen gas that's being collected. So when the reaction is over, you would seal this off right here. You'd put like something over the mouth of it, and you'd pull it out and you'd measure how much water is left. Because if you know how much water the whole thing was, and you know how much water is left, the rest of it is the oxygen gas. So that's one way to do it. Another way is we actually have at school a gas collecting tube. Okay, and the gas collecting tube, you would fill all the way up with water, just like they did here, but it actually has markings on it where you can read volume in milliliters, and so you wouldn't have to do all that extra work. The empty space would read you your volume once the water was out. So this is like called the gas collecting tube, and it has actual markings like your graduated cylinders do, and like your burettes do. So that's another way to do it, to collect the oxygen gas and measure the volume of it that is collected. Again, this works because most gases are generally colorless and they're less dense with water, so you can't really, it's harder to measure them if you can't see them. So that's why this method is important. Now, the other important thing is the fact that when you collect a gas over water, oops, I want to do a little blue. Water on its surface has some of its molecules that are in the vapor or gas state. Okay, so because it has some particles that are vapor, that are water, we have to account for them. So the total pressure in here is because there's oxygen and there's likely a there is a tiny bit of pressure that comes from the fact that there's water in this container. So to get to know the total pressure, if you know the total pressure, you have to know that inside the container, the total pressure is a contribution of both of these gas particles. Now, if the water's like room temperature, this number isn't gonna be big, right? It doesn't exert a lot of pressure at room temperature, but it exerts enough that we have to account for it. Okay, so we're taking potassium chlorate and we're heating it. I give you the temperature it's happening, and this is the total pressure of the room. And then I tell you the volume of gas collected was 0.650 liters. And then I tell you the vapor pressure of water. So the pressure that water contributes, this tiny little bit of pressure at 22 Celsius, is 19.8 torr. That's not a lot of pressure, right? Atmospheric pressure is 760, but it's enough that we have to account for it. So when I ask you to calculate the partial pressure of the oxygen gas, I have to take, remember, total pressure is the partial pressure of oxygen that's collected plus the tiny bit of the fact that there's water in there. So you take total pressure and subtract water and you'll get the oxygen gas. So total pressure is 754 and you subtract 19.8, and so the partial pressure of just the oxygen gas in that container is 734.2 torr. Now, they sometimes refer to this as dry gas or dry oxygen gas, and the reason it's dry is because you've taken away the water, the tiny bit of water vapor that contributes, but remember that it is in there and we have to account for it. So here's why this is important. If you're going to use like any kind of gas laws, you need to use the pressure of the dry gas, not the total pressure of the room. So that's where you're going to have to be very careful. So they want you to calculate the mass of potassium chlorate in the sample that was decomposed. So I have temperature, I have volume. This is my pressure of all of these belong to oxygen. This doesn't belong to oxygen. This is the total pressure in the container. That belongs to oxygen and water. So that's why we use this pressure. So what can I get? If I have temperature and I have pressure and I have volume, what can I find? I have P, V, and T.
You can find moles.
You can find moles. Beautiful. And let's talk about why this is important. Well, if you look, so let's write out the reaction real quick. It's KClO3 decomposing to KCl plus O2. Oops, sorry about that. 2, 2, 3. All of the information they give you is about oxygen, its volume, its temperature, its pressure, but they want to know about KClO3. So moles is a great tool, right? Because I know I'm going to have to eventually do mole ratios if I want to jump from oxygen over to KClO3. So I need to get in moles to be able to do that. Well, if I look at PervNert, I have pressure, I have volume, I have T, you always have R, so I can rearrange to solve for moles. PV over RT is moles. So what's the pressure? Well, that was the 732.4, or is it 734.2? Did I say that backwards? Oh. 734.2. I did say it backwards. $734.2 torr. Okay, there's my pressure. What volume was collected? Well, it was 0.650 liters of oxygen gas collected. If you go on your equation sheet, go to the gases part, which is right here. You scroll down. Here is the unit for the R constant in torr, 62.36. So 62.36 liter times torr over mole times Kelvin. And temperature in Kelvin, oh, I don't even remember. Was it 22 Celsius? So that's 295 Kelvin. All right, let's check out units and how they work out. So torrs cancel, liters cancel, Kelvin cancel, and you're left with moles. So I'm going to give you a second to calculate that out, and I'm going to do it myself too. Hit that divide button twice to minimize any calculator issues. 0.02594. Okay, here's the thing. You don't want to round right now. You're not finished. So this is O2. All of this information belong to O2. You're not finished, so you want to like keep the whole number in your calculator. You can write out a couple of digits, but you're not going to round here. You're not done. You don't want to round until the very, very end. So this is moles of O2. Well, now that I'm at moles of O2, I can do stoichiometry. So this is the old stuff that we used to do. 2594. Sorry about that. That's a weirdest 9. 2594 moles of O2. Let's have some fun. Let's do some Halloween colors. Okay, for every 3 moles of O2 that react, 2 moles of, that are produced, 2 moles of potassium chlorate react. 3 moles of this being produced for every 2 moles of potassium chlorate reacting. And now you can just turn moles into grams because they asked for mass. 1 mole of potassium chlorate is 122.4 5 grams. And I think, if I'm not mistaken, this answer was like 2.11 grams or 2.12 grams, something like that. You guys can correct me if I'm wrong. I'm going to give you a second to calculate this all out, please.
I got 2.12.
Okay. Okay, so what we are doing actually is called Dalton's law of partial pressure. What that means is that total pressure when you're collecting a gas over water is the pressure from whatever gas you're collecting plus the fact that there's a little bit of pressure that comes from the water. So Dalton's law of partial pressure just means that the total pressure in any container is a combination of the sum of all of the pressures of the gases in that container. So if you have 4 gases in a container, all 4 of them contribute to the total pressure. Okay, and then ideal gas law with multiple gases is if you want to find out the total pressure, you can, if you know the moles total, you can find out the total pressure by plugging in just the total moles of every single gas present in the container. Or you could find each gas's pressure individually and add them all up. So if you look on your equation sheet, you will see Dalton's law of partial pressure right here. Oh, hey, what? No. Why did it do that? So here's Dalton's law of partial pressure right here. Total pressure is a combination of the pressure of any gases that are in the container. All gases contribute to the total pressure if there's more than one in the container. Okay? So let's go back. So I say a gaseous mixture made from oxygen gas and methane gas is placed in a container that has a volume and a temperature. What is the partial pressure in atmospheres of every single gas, and what is the total pressure? Well, if you find the partial pressure of every gas, you can just add those gases together to get the total pressure. And then I'll also show you an alternate way. However, you can't use grams. Ideal gas law doesn't have grams in it anywhere. So we're gonna, so it's 6 grams of oxygen and 9 grams of methane. So if I want to find, right, PV equals nRT. If I want to find out about oxygen, I just plug all of oxygen's information into here. Partial pressure of oxygen is going to equal the moles of oxygen, RT over V, right? I just rearrange this. So the same thing over here. Partial pressure of methane is going to be moles of methane, RT over V. So you have to turn these grams into moles. This is 32 grams per 1 mole, and methane is 16.05 grams per 1 mole. And then you go ahead and plug in. So the moles of oxygen, I think, is 0.1875, if my memory serves me right from last class. My R, I asked for the pressure in atmosphere, so you're going to use the equation on the equation sheet that's in atmosphere. So the R constant for atmospheres is right here, 0.08206. Liter atmosphere over mole Kelvin, crazy units. The temperature was 0, right? So that's 273 Kelvin. And then, what was the volume? I don't remember. Is it 15? 15 liters, good. So, calculate that out. So this is a great question that Martin just asked. He said, does Dalton's law, or it doesn't apply if gases are reacting? We're going to do that later. It sort of applies, but a little bit differently. You would have to figure out how much of each gas is reacting and what you have at the end. So we actually will end class doing a problem like that. It's a very good question. All right, so the partial pressure of oxygen. What did you guys get? I mean, I have the answer on there, right? 0.280. So then you just do the same thing again, but for methane. Now, nothing else changes. So like, right, the R constant doesn't change for the methane. The temperature is still the same. The volume is still the same. The only thing that changes is how many moles of it you have. So 19 divided by 16, blah, 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 is like 0.56 something. Remember, you don't want to round till the very end. So this is going to be for methane, the 0.56 something, 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 56. And then you plug that in. So I'll give you a second to do that. You should get this 0.838 atmospheres, and then total pressure is just the sum of all of the pressures of every gas in the container. There's 2 gases in the container, so it's this partial pressure of oxygen, partial pressure of methane, add them together, and that is total pressure. Now, there's another way to get total pressure that I just mentioned to you. Does anybody remember what it is? I'm just telling you an alternate way you could find total pressure. Remember, total pressure is just moles total of every gas there, RT over V. So you would plug everything in the same except for moles. Oops, sorry. Because you're going to do moles total. Well, if this guy was 0.1875 moles, plus this guy was 0.56 something something moles. I don't know, you got to add it up. So 0.1875 plus 0.56 something something, it's like 0.74 something something. So now P total has moles total. This is the oxygen's moles. This is the methane's moles. If you use the whole number, it's like 0.7482 something, blah, 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 blah moles, okay? And you should still get really, really close to the same exact pressure for total pressure. Total pressure involves total moles, but this is the same, R is the same, T is the same, volume is the same. Any questions about that? This is just an alternate way to find total pressure. Both ways work. You can use Dalton's law of partial pressure, or you could use Pervnert to find total pressure. All right. So having done this example, I'm going to kind of start you off on this one, and then I'm going to ask you to please work solo. So I give you partial pressures in atmospheres, and they're all in the same container. So this container is 10 liters, and they're at a certain temperature, 65 Celsius, and they want to know what the total pressure is. So I need to know hydrogen, and I need to know helium, and I need to know methane. I gave these numbers to you to be kind of like nicer numbers. Remember that to do this, so like the partial pressure of hydrogen is moles of hydrogen, RT over V. Again, this is just Pervnert rearranged. And then you would do this again, but for helium, partial pressure of helium is moles of helium, RT over V. And then you do it again, but for methane, moles of methane. Now, I want to point something out before I let you kind of take a couple minutes to work on this. 4.04 grams of hydrogen gas, and hydrogen gas is 2.02 grams per mole. So how many moles is that? Just 2 moles of hydrogen gas. 8 grams of helium, and helium is 4 grams per mole. So how many moles is that? Look at the answers for hydrogen and helium. They exert the same amount of pressure, and the question is, why?
Same amount of moles.
Same moles of gas. Well, exert the same pressure as long as the conditions are all the same for everything. Because same amount of moles means you have the same amount of molecules of hydrogen as you do atoms of helium. So if you have the same amount, then they're going to exert the same amount of pressure. So I'm going to give you about 3 minutes to go through and answer all these questions, and then I'm going to go back and talk about it. All right, so to find the P total, you can take all the partial pressures and add them up, 5.55 plus 5.55 plus 2.77, and that would be the total. Or you can use Pervner with total moles. Okay, and so this would be P total, and this would be N total, and this is 2, and this is 2, and this one was 1. So 2 plus 2 is 4, plus 1 is, this would be a 5 for your moles. And then you could find P total that way. Plug the R and the T and the V in. Now I want you to notice something else. This was 1 mole of methane. Notice it's half the amount of both helium and hydrogen. So that means you have less methane molecules floating around. And it contributes half the amount of pressure. Okay? Any questions on that?
So we do our sig figs according to the little chart of like the grams of gases, or?
Well, yeah, so these are, this is 3 sig figs, 3 sig figs, this is 4 sig figs. And then what happens when you add them all together, you follow the decimal place.
Oh, okay. Yeah.
You're welcome. All right. Okay, so this concept of mole fraction, for some reason, again, kids kind of find this a little bit confusing. All it means is what percent or fraction of the gas is a certain gas. What percent of the total is a certain gas? So if like 50 kids out of 300, no, sorry, 50, like 50% out of 300 were girls, 150 of them would be girls, all right? So it's the same concept. So pressure of any gas equals the mole fraction of that gas times the total pressure. So if you go on your equation sheet, they also give you this equation. Sorry, I gotta move this. It's in my way. So here it is, right here. This is the partial pressure of any gas equals the total pressure times the X, means mole fraction of A. Now we're going to talk about this part in a little bit, but I just wanted to show you where it is on your equation sheet. So mole fraction can be written as a decimal, or it's sometimes written as a percentage. So let's talk about this. How much pressure does nitrogen gas contribute to the atmosphere in our room right now, given that nitrogen makes up the majority of our atmosphere, 78%, and the pressure of the room at this given moment is about 763 torr. So you go, okay, well, the partial pressure of any gas, in this case it's nitrogen, is equal to the fraction or the percent of it times the total pressure. So the partial pressure of nitrogen gas equals, now this is called mole fraction, but it also can be considered a percent. So you could write it as 78 over 100, because that's what 78% is, or you could just write it as 0.78. It doesn't matter. I'll write it as 0.78 up here. It's the same thing, okay? Times total pressure, which is 763. So 595 torr is how much pressure nitrogen gas contributes of the 763. This is what 78% of 763 is. That's exactly what you're doing. So again, it's the majority of the pressure, right? Because it makes up way more than half of the atmosphere. It makes up the most of it. The rest of it's oxygen and then like a tiny little bit of argon. Okay. So this one says the partial pressure of oxygen was observed to be 156 torr in air. So this is a lot less pressure. Well, that's because oxygen doesn't make up the most of the air, with a total atmospheric pressure of 743 torr. Calculate the mole fraction of oxygen present. Well, there's an equation for this. Partial pressure of any gas, and in this case it's oxygen, equals the mole fraction of that gas times total pressure. Well, I have the partial pressure of oxygen. I have the total pressure. Rearrange and solve for mole fraction. So 156 for oxygen. And then, right, you divide both sides by PT. Divided by 743. So 156 torr out of the 743 torr is 0.210. That's the mole fraction, which would be 21% of the pressure is coming from oxygen, and the rest is coming from nitrogen, and then like a tiny little bit of argon, and probably some other gases too, but those are the three most abundant: nitrogen, oxygen, and argon. Questions so far? Okay, so here's what I want you to do. I don't want you to do this mole fraction for O2. However, on your own for right now, I would like you to find P total, partial pressure of oxygen, and partial pressure of hydrogen. It's not like what we just did. It's like the things we just did before we talked about mole fractions. So you can do PT, partial pressure of O2, and partial pressure of hydrogen. We'll talk about the X of O2 after. So I'm going to give you a couple minutes to work on this problem independently. Okay, so hopefully you were able to find the partial pressure of oxygen and the partial pressure of hydrogen, and then once you know total pressure, you can just add these two guys together to get this number. Now, you could also, to find total pressure, you could have done this: P total equals 6, because that's 2 moles plus 4 moles, so that's N total. And then plugged in the R and the T and the V. Okay, that's the other way to get P total. Now, in this problem, there are two different ways to get mole fraction. So the first way that we've already talked about is this equation. Partial pressure of any gas, which is O2 because that's who it asks for, is equal to the mole fraction of that gas and total pressure. Now, because you went through all of these steps, you have this and this. You have the partial pressure of oxygen, you have the total pressure. So the partial pressure of oxygen is 9.80 divided by, right, you would move total pressure over here. The total pressure in the container is 29.4, and that would give you 0.333, which means of the 29.4, 33% of the pressure is coming from oxygen. This is one way to do it. There's actually an alternate way to do it. If you look on your equation sheet, they tell you that mole fraction literally means moles of the gas, whatever gas you're looking for, over the total number of moles of all gases only in the container. So let's see. Mole fraction of O2 is moles of O2 over total moles. So what is my moles of O2? Well, it was 2, right? Divided by hydrogen was 4, so the total moles was 6. 2 divided by 6 is 1/3. 1/3 is 0.333. So there's two different ways you could have done the mole fraction. Any questions on that? All right. So this is just a conceptual question. So I'm going to give you a second. I have the same volume, so all of these are the same size container. Okay. I have 172 Kelvin, so they're all at the same temperature, and I want to know which one has the higher pressure. This is similar to percent composition, but it's more like percent of the total, like just like any other percentages would be. Like, how much pressure is oxygen contributing? What percent of pressure is oxygen contributing? What percent of pressure is nitrogen contributing? That's the concept. So now these are all the same size, they're all at the same temperature, and I tell you how much of each gas is in container by mass. Does anyone think they know which one is going to exert more pressure? when we talk about gases and pressure, is mass going to help us? The pressure doesn't directly depend on mass. It depends on what?
Moles.
Moles. So how many moles is this about?
1. They're all the same. Yeah.
So if you have the same number of moles, you have the same number of, this is 6.02 times 10 to the 23rd molecules of oxygen. This is 6.02 times 10 to the 23rd atoms of helium. This is 6.02 times 10 to the 23rd molecules of hydrogen. So their pressures are all the what? Same, because they're all under the same other conditions. All of these guys' pressures are the same. None exerts more pressure than the other. They're the same temperature, the same size container, and the same amount of stuff by moles or molecules or atoms, however you want to look at it. Questions on that? They are equal. Good job, guys. So, this is where kids get a little bit frustrated. So I want to talk through, and I want you to listen and take good notes, right? I try to explain how to know how to do the problem, like strategies and ideas, because it's not that you guys can't do this math. Oh, hold on 1 second. Sorry, I got a delivery. My dog. So it's not that you can't do this math. It's knowing, like, what do I plug into? There's so many equations. This is so confusing, okay? So let's look at this problem. So you have, shh, Todd. So they want you to find the total pressure, the partial pressure of oxygen, the partial pressure of nitrogen, and the mole fraction of oxygen, which we'll do last. That's a new concept for us. For the following container after the valve is open. I know this is off. It says let the pressure be in atmospheres. So I want to know the pressure in atmospheres, okay? So let's look at this. We have a container. It's 5 liters, and it has nitrogen gas in it, and it's at 2 atmospheres, this container. Then we have this container. It's 3 liters, and it's oxygen gas, and it's at 1 atmosphere. And then this is a valve that opens and shuts. So like right now, these are closed. This is what they are when the valve is closed. Okay, we've been using Pervnert a lot, right? So I'm going to reference this for a second. You go, okay, there's like 2 volumes and 2 pressures, and like that's not what we do when we use Pervnert. You can't have 2 of anything when you use Pervnert. Does anybody remember what we used when we had 2 of something? 2 or more, I guess, of something.
Combined gas law.
Combined gas law. So let's look at that. Now, do they mention anywhere? So I see pressures, I see volumes, okay? Do they mention temperature anywhere? No, so it's assumed constant. Do they mention moles, or do they have like grams to get us to moles? Do they have any way to get us to moles? What's that? No, we have no ways to get to moles. So we're just looking at pressures and volumes. So the whole concept is if you open this, what happens? Just conceptually, what's going to happen? The gases are going to what? Mix, right? They're going to diffuse. If they're blocked, they won't mix. But if you open it, most gases move randomly and they'll mix on their own. But mathematically, what's changing when you open this valve?
The
Volume. They have more space to move around in. Both of them do. Originally, they're confined like to their own rooms, right? This guy has a 5-liter room to hang out in. This guy has a 3-liter room. But when you open this, How much room do they have to have? Ugh.
8 liters.
8 liters, good. This is 5 liters, this is 3 liters. If you open this, they have the whole thing to move around in, and the whole thing would be a combination of 8 liters. So, having said that, what variable in this equation does that belong to? Which one of these letters?
V2.
V2. That's my final volume, is 8 liters. So how do I do this? Well, you have initial starting amounts that are different for each gas. So you have to do P1V1, P2V2 for this guy. And then separately, you have to do P1V1, P2V2 for this guy. And what they have in common is the V2. It should be 8 liters because both of them, once this valve is open, are in 8 liters of space. But they don't have same starting conditions. So you have to do P1V1, P2V2 twice. I'm going to give you a minute or two. I'd like you to do that. So just focus right now on these three. We'll talk about mole fraction in a second. So we can only use this, I have to repeat this because I hit the record button, equation instead of the moles fraction equation that's on your equation sheet, because we don't have moles, okay? So if we don't have moles, we can't plug into this one. This is our only option to find mole fraction. So you rearrange it, you divide both sides by PT. Here's your partial pressure of oxygen on the top, divided by PT, there's your total pressure on the bottom, and you get 0.231, which means 23.1% of all the pressure is oxygen. So by default, the rest of the pressure is coming from nitrogen. All right. So mole fraction and limiting reactant. Oh boy. Limiting reactant. So the following reaction goes to completion, and I give you a volume and a temperature, and then I give you the reaction, and then I tell you you have 0.25 moles of hydrogen and 1 mole of chlorine. Now, I told you it was a limiting reactant, but the hint that it's a limiting reactant is I have amounts of both of these and nothing else. So if I have amounts of both of these, I'm going to have to figure out who the limiting reactant is. So they want you to find the mole fraction of all gases. So Martin, this is what you're asking about. Find the mole fraction of all gases present after the reaction is over, not at the beginning. So let's talk about this. Let's see, hopefully I have you have H2 plus Cl2 makes 2HCl, and these are all gases. I know you think that's hydrochloric acid, but under certain conditions, you can get it to turn into a vapor, okay? And now, because it's a limiting reactant, I'm going to use an ice chart just to organize my math. So it was, I got to go back, 2.5 of hydrogen and 1 of chlorine. So 2.5 of hydrogen and 1 mole of chlorine. Now, we haven't talked about products so far with ice charts, but theoretically, you shouldn't have any product before, right? This means initial, before a reaction starts. So I'm going to put a 0 there. Now, limiting reactant, look, I have amounts of both reactants. This is a 1-to-1 ratio. So if this is 2.5, this needs to be 2.5. It's not. It's less than 2.5. So this is my limiting reactant. So how much, right, this is my change column, or row, I should say. How much do I lose of my limiting reactant? Well, theoretically, all of it. The whole point is that you don't have any left at the end. Now, if you remember, this is where you do your where you do your stoichiometry. Okay? Sorry, I cannot draw straight lines apparently. Wow. So if I know that how much of this reacts, I can do mole ratios to figure out how much of this reacts. And if I know how much of this reacts, I can do mole ratios to figure out how much of this is produced. So 1 mole of chlorine is reacting, aka all of it. For every 1 mole of chlorine that reacts, 1 mole of hydrogen reacts. So this is also minus 1 mole. So if I had 2.5 moles at the beginning and I lost 1 mole, you take these two rows and you combine them and you end up with 1.5 moles excess hydrogen gas. Now this is something that we haven't done before. So now I have to go to products. So for every 1 mole of chlorine that reacts, and again, you're using your limiting, 1 mole of chlorine reacts and 2 moles of HCl are produced. That's the mole ratio. So 1 to 2. So 1 times 2 is 2. So this is 2. Now, products are gaining, right? That's the whole point, is that these guys get consumed because this guy gets produced. So this is a plus sign, not a minus sign here. So 0 and 2 is 2. All right. So they want the mole fraction of every gas. Okay. So we have the moles at the end. 1.5 plus 0 plus 2. So there's a total of 3.5 moles of gas. All gases. Specifically, it's the hydrogen and the HCl. That chlorine really isn't in there. So what's the mole fraction? Well, mole fraction of hydrogen is going to be moles of hydrogen over total moles of gas. And then the mole fraction of the HCl is going to be moles of HCl, which is 2, over total moles. Questions so far? So let's look back. There's your mole fractions right here. So I'll give you a second to calculate that. So that was A. So B says find the total pressure in atmospheres in the vessel after the reaction. So there are 2 ways to do this one, actually. Oops. So there are 2 ways to find the total pressure. So you could do the partial pressure of hydrogen gas. You could do it this way. Wow, why is that doing it like that? Equals moles of hydrogen gas after the reaction's over, RT over V. Because if you look back, they gave you all that info. Look at, they gave you the temperature, 78. They gave you the volume, R is a constant. You have moles now. So you would plug and chug into here. And then you could do the same for the HCl. So the partial pressure of HCl would be the moles of HCl after the reaction is over, RT over V. You could do it this way. And then you could get the partial pressure of hydrogen and the partial pressure of HCl, and then you would add them together to get total pressure. Or you could just straight off the bat get total pressure by including total moles in the ideal gas law. Oops. nRT over V. So total moles is 3.5. This way takes less time technically. So 3.5 and then RT over V. Either way, you can do this and then add them together, or you can do just plug straight into one permanent with total moles included in there. Again, you can do whichever way you feel the most comfortable. Oops. What is this? What am I doing? What is happening right now? I don't want to pull. Okay, thank you. So I'll go back so we can look at what the answer was. So total pressure is 16 atmospheres. Questions so far? Okay, so let's talk about find the partial pressure of hydrogen in atmospheres after the reaction is over. Okay, so there are 2 ways to do this. Oops, sorry. We already said that we could do it this way. This is one way to do it. Find the partial pressure of just hydrogen. Moles of hydrogen, which would be 1.5, and then the RTV are all given. What's the other way we could do it? Partial pressure of any gas, this is on your equation sheet, equals the mole fraction of that gas times total pressure. So we know all of these. We have moles of the hydrogen and we have total pressure, so we could do this one also. So this would be, what's the mole fraction of hydrogen? Well, it's 1.5 moles of it out of 3.5 moles. And total pressure, we just found to be 16. 16. So this is an alternate way. This way or this way. We have enough info in this problem to use either one. Any questions so far? We're almost done.
Wait, so do you use the moles? Oh wait, never mind. I thought H2 was a limiting reactant. I was like, wouldn't it be 0? Never mind.
Yeah, it's a limiting reactant. So right, it's kind of, they obviously didn't ask for chlorine because it's not, technically it should be 0 because you shouldn't have any of it.
Yeah, sorry.
That's okay. All right, let's try one more. So here's just the ice chart. I already did this for you, but here it is. All the numbers. Now let's read this one. So you have A and B, some random gases reacting to make C and D, and I give you initial. Now, if you see the words initial in a problem, sometimes it's a hint that ice charts could be helpful. Not always, but sometimes. So initial pressures. So I give you amounts of this and this. Now notice that they're not in moles. So here's what I need to tell you. If you have a chemical reaction, okay, and they don't tell you anything about temperature or anything about anything else. Okay, so the word rigid vessel means the volume is constant. The vessel doesn't expand or deflate or compress. So rigid vessel means volume's constant. The vessel doesn't change volume. Obviously, you're assuming temperature is not changing. So instead of plugging moles into my ice chart, I am allowed to plug in pressures if everything else is staying constant. Okay, so A is 3.5 and B is 2.6. So they say this was 3.5. Let's see. 2.6. Oops. All right. Initially, you should not have any products at the beginning of a reaction because it hasn't started yet. So at first glance right now, so I'm plugging atmospheres into here. Yes, I am. That's because the container is rigid, which means it's not changing volume. I don't mention anything about temperature, and so it's not changing, so I can use these atmospheres just like moles, including the ratios. So then the question becomes, is it a limiting reactant problem? Well, it looks like it, except for one thing. I actually give you an additional piece of information that I did not give you in the last problem. I asked for the partial pressure of C when the pressure of A has decreased to 1.5 atmospheres. So this is my ending pressure. So meaning they're like at a spot in this reaction where it's probably not over. They just want to know at this given moment when A is 1.5 atmospheres, what is C? So the reaction has not gone to completion is the point. So it's not actually a limiting reactant problem. So what do? Well, I plug in for A 1.5. That's what it's decreased to. So in order to find C, how much did it change by? Well, 3.5 minus what? 2, right? So it lost 2 atmospheres to get to be 1.5. Now, this change row is your stoichiometry row. So you will use this number to find out any other numbers. You can find out this guy and this guy and this guy. Now, specifically, they asked for C. So if you're losing 2 atmospheres of A, for every 1 A that reacts, 2 C are produced. So 2 times 2 is 4. So, oops. Now, I'm gaining, because it's a product, 4 atmospheres. Okay, so 0 plus 4 is 4. So the partial pressure at this given moment is 4. Now, could I ask you to find the rest of them? Sure. What is this ratio? This is 1 to 1. So if I lose 2 here, guess what? I lose 2 here. I didn't ask you, I'm just showing you. A and D is also 1 to 1. So if I lose 2 here, I would gain 2 here because it's a 1 to 1 ratio. So 2.6 minus 2, this would be 0.6. I didn't ask you for these, I'm just showing you. This would be 2. 0 and 2 is 2. So this could be a way that like they could be like, oh, what's the total pressure at this given moment? And yes, that one of my reactants hasn't run out. That's because they gave me this extra piece of information. If that last sentence was not in there, if this was not here, and they said, what is the partial pressure of C? And then they didn't give you this last part right here. You would treat it like a limiting reactant problem. But because they did, you don't. They gave you an extra value you get to plug in. Okay, last thing, and then I'm setting you free. So I fixed, so this is the ice chart with just partially just the answers they wanted filled in. They only asked for C in the problem, but I just want to show you that it is possible to get all of the other answers as well. And this box is a reaction arrow, by the way. So my MCQ for all my other classes, I fixed this. Sorry about the arrow. That's an arrow that's in the wrong spot. My formatting can be a pain sometimes. Okay. So nitrogen and hydrogen gas are added to a previously evacuated, so that just means they've taken all the air out. So all that's in there is just nitrogen and just hydrogen. 10-liter rigid, that means it's not going to change shape no matter what. It's going to stay all 10 liters the whole time. Insulated means heat's not going to escape, so it's going to be 25 Celsius the whole time. They're trying to tell you volume and temperature are constant. And they give you initial partial pressures of each reactant. So 1 atmosphere of this guy and 1 atmosphere of this guy. And they want to know if the reaction could go to completion, okay, what would the final total pressure in the container be? So this is a gases without a calculator, right? That's what MCQs are. So again, this is a limiting reactant problem. They give you amounts of both reactants. They don't give you any other information. So I'm going to set up this ice chart. Now, again, I get to plug atmospheres into here because temperature and volume are not changing. Theoretically, you should not have any product at the beginning of a reaction. And you go, okay. In the last problem we just did, they gave you like a number down here. They said, oh, and find out when you know this number. Well, I didn't give you that in this problem. So this is a limiting reactant problem. Well, if this is a 1 to 3 ratio, if this is 1 atmosphere, this should be 3 atmospheres. And it's not. It's less than 3. So less than, so this is my limiting. So how much do I change? How much do I lose of it? I lose all of it. I shouldn't have any of it left at the end. So now, remember, this is your stoichiometry row. This number, this 1 atmosphere, not this one, I'm not using this 1 atmosphere. I realize all of these have 1 atmosphere, but it is specifically this one I am using to do stoichiometry. So 1 atmosphere of H2 is lost, right? And for every 3 H2s, there's 1 N2. So this is losing 0.333333 atmospheres. Okay, now you can either use this guy or this guy to determine ammonia. Once you know any of these in the C column, you can use to find the other. Mathematically, I'd probably use this guy because this is a 1 to 2 ratio, meaning this is 0.33 times 2, which is going to be 0.666666, whatever, 7. Okay. Or you could go back and use your limiting reactant. So 1 atmosphere of hydrogen is reacting. And you would say for every 3 hydrogens that react, 2 ammonias are produced. 1 times 2 is 2. 2 divided by 3 is 1. 2 divided by 3 is obviously 2/3, which is 0.66666. It's still the same number. What I'm saying is it doesn't, once you know one of the C's, you can use any of the C's to find the other substances. So 1 minus 0.33 is 0.66667-ish. 0 and 0.666 is 0.6667-ish, okay? And then this is 0. So this is 0.66 atmospheres plus 0 plus this is total pressure. So that adds up to like 1.2. If you would round this to like 0.67 and 0.67, it'd be like 1.3. So is there an answer that's close to that on my slide that I fixed? That is C. 1.3 is the total pressure after the reaction goes to completion. I'm going to show something. I didn't show this in my other classes, but hopefully kids will watch the video. Okay, this is not true, but I want to show you something. Let's say somehow I had silver available in my products. And I wanted to find total pressure. So I had silver over here. For whatever reason, I had some sort of solid over here. And that's because it was over here somewhere too. Okay, whatever. Would I care about any of silver's information for this problem? No. Why, Micah? Why don't you care anything about silver's information? If I want to find pressure, pressure belongs to what kind of substances? Gases, right? You can't plug things about silver in and add them up. I mean, you could solve some stuff, but you're not going to plug stuff in about silver to solve for pressure. I mean, like maybe you could find mass or something, but like if you're trying to find pressure, you wouldn't care anything about any solids whatsoever. Share that with your friends from other periods. I'm probably going to send it out in a message too because you want to make a note of that. You can have solids produced and you can also have gases. The only thing that can be plugged into Dalton's law of partial pressures, ideal gas law, combined gas law, are gases. You can't start throwing solids or liquids or anything aqueous in there. Only gases.